Başlıyorum.
Bir saniye. Şimdi yayına giriyoruz. Evet, tamamdır. Canlı yayın başladı. Evet, başlayabiliriz.
Merhaba arkadaşlar ve merhaba hocam. Bugün bizimle beraber Antigona hocamız var ve bize Galois Theorem and its Applications adlı sunumunu yapacak. Şimdilik sözü size bırakıyorum hocam ve sadece şunu ekleyebilirim. Sunum sırasında bir sorunuz olursa chatten yazabilirsiniz. Sunumun sonunda hocamıza ileteceğiz. Bu kadar.
Evet, ekran paylaşımını yapabilirsin Antigona. Başlayabiliriz.
Şimdi yapacağım. Ekranımı görebiliyor musunuz?
Geldi.
Görebiliyoruz.
Sunumu İngilizce'de yapacağım. Okay, today I'm going to talk about Galois theory and one of its applications. My main theory here is that to explain to you some results about fundamental theorem of Galois theory, which sets a one-to-one correspondence between group theory and field theory, such that we can find necessary and sufficient conditions for a polynomial over a field F to be solvable by radicals. First, I'm going to give you some definitions. A polynomial ring f adjoint x in X over the field F is the set of all polynomials in X of the form here f of x is equal to a sub 0 till a sub n x to the n, where the constant terms are in our field F. If this constant a sub n is equal to 1, then our polynomial is called a monic polynomial. When we think about polynomials, we always try to decide if they are reducible or irreducible. For a polynomial in our polynomial ring, we say that it is reducible over the field F if we can factor f of x as a product of, let's say, two polynomials g of x and h of x from the same polynomial ring of strictly lower degree. Otherwise, if f of x is not reducible, then we say that it is irreducible over the field F. A way to test if a polynomial is irreducible is Eisenstein's criterion, which gives us a polynomial over the polynomial ring of integers. That means that all the constant terms are integers, or of degree greater or equal than 1. And if there is a prime p such that p squared doesn't divide a sub 0, p divides a sub I for I between 1 and n minus 1, and p doesn't divide a sub n, then we can say that the polynomial f of x is irreducible over the field of rational numbers. As we look carefully at this theorem, this is not an if and only if statement, because if Eisenstein's criteria fails for all the primes, that does not necessarily imply that f is reducible. As an example here, I wrote the polynomial x squared plus x plus 1. No prime p works, but still we cannot factor this polynomial f of x over the rationals. Another example where we can say that x squared minus 2 is irreducible over q by using Eisenstein's criterion is if we set p equal to 2. Let's see, like if we set p equal to 2, then 2 squared, which is 4, doesn't divide 2, and 2 doesn't divide 1. So we can immediately say that this polynomial is irreducible over the field of rationals. When we cannot find the roots of the polynomial over the field that it is defined, we can always look at its extension. In your left, you can see this diagram where both E and F are fields, and F is a subfield of E. Then E is called an extension of F. We regard this E as a vector space over the field of F, and we denote it by this notation. And the dimension of E over F is denoted by this notation here. We have different kinds of extensions. One of them is algebraic extension. Okay, so we call this E, where F is a subfield of E, an algebraic extension of F if each element in E is algebraic over F. and an element is algebraic over f if it is a root of this polynomial p of x here. If this p of x is monic and irreducible polynomial over f, then, and it has alpha as its root, then this polynomial is called the minimal polynomial of alpha over f. Sometimes there are fields that contains all of the roots of the polynomial that is defined over that field, and such fields are called algebraically closed fields. So a field f is algebraically closed if for any polynomial f of x in our polynomial ring, all of the roots of f of x lie in the field f. Now, an extension E of a field f is called algebraic closure of f if it has these two properties: if it is algebraic extension of f, and if it is algebraically closed. Every field f has an algebraic closure, and algebraic closure of f is unique up to isomorphism. We denote it by E bar here. As to see it more clearly, I wrote some examples. The field of rational numbers is not algebraically closed because, as we can see, the polynomial x squared minus 2, it has a root which doesn't belong to rational numbers, which is square root of 2. Real numbers 2 is not algebraically closed because there is a polynomial x squared plus 1, which has a root that it's not in the real numbers. But the field of complex numbers, it is algebraically closed. This is actually the fundamental theorem of algebra. It contains all of the roots to all of its polynomials that are defined over the field of complex numbers. When we find the root of our polynomial, we can see if it's factored over some field. So if we have a polynomial in this polynomial ring f adjoint x of degree greater than 1, then an extension k of f is called the splitting field of f of x over f if that polynomial f of x can factor into linear factors over that polynomial ring k adjoint x, where alpha i's are in k. Sorry, this must be k, not k adjoint x. And 2, this extension is generated by f and alpha i's, where alpha i's, as I said, are the roots of our polynomial f of x over f. So in the splitting field, k over f, our polynomial can be factored into linear factors. As an example here, I gave this x to the x cubed minus 2, which is irreducible over the field of rational numbers. By taking p equal to 2, then it follows by Eisenstein's criterion. One of the roots of this polynomial is the cube root of 2. Then we can adjoin this root to rational numbers and create an extension in which this polynomial has a root. But still, this polynomial has a complex root that it's not contained in the field q adjoined to cube root of 2. So that's why we can create another extension that contains the root of this polynomial. And this polynomial here can be written into linear factors in this way, like x minus cube root of 2, x minus alpha times x minus alpha conjugate, where alpha is the complex root of this polynomial. In our case, this rationals adjoin cube root of 2 and alpha, it is a splitting field of p of x over q, because as we can see, the polynomial can be written as a factor, as a product of linear factors. Another extension here that I'm going to present to you, it's called normal extension. An extension E of f is called normal extension if every irreducible polynomial in f adjoint x that has a root in E splits into linear factors in E. If you look at our previous example, we can see that q adjoin cube root of 2 and alpha, it is a normal extension of of p of x over q. Because why? This x cubed minus 2 has a root here, and it also can be written as a product of linear factors in the same polynomial ring. But we have to be careful because this might, like, somebody may ask, what is the difference here about like the splitting field and the normal extension? If this extension is finite, then we can say that every normal extension is splitting field. It's an if and only if statement. But if our extension is infinite, then we cannot say that. For example, real numbers is not a normal extension of rational numbers, because the same polynomial that has a root in the real numbers, cube root of 2, it doesn't split into linear factors there because it also contains a complex root. When we're talking about the roots of polynomials, there are simple roots and there are multiple roots. An irreducible polynomial is called separable if all of its roots are simple. So an extension E of a field F, it's called separable extension if all of its elements are separable. And an element of E, it's separable over F if first of all, it's algebraic over F, and its minimal polynomial is separable. That means that the roots of its minimal polynomial are all simple. We have two important remarks here according to separable polynomials. Any polynomial over a field of characteristic 0, it's separable. Thus, if F is a field of characteristic 0, then any algebraic extension of F is separable. And B, irreducible polynomials over finite fields have distinct roots. Hence, any algebraic extension of a finite field, it is separable. Till now, we saw normal extensions, separable extensions, algebraic extensions, and also finite extension. An extension E of a field F, which is finite, normal, and separable, it's called a Galois extension of E. Now we are going to look, to take a step into group theory here by considering these extensions of F. The group here denoted by this notation is called the group of F automorphisms of E. That is, its elements here are all automorphisms that map E into E and keep all of the elements of F fixed. If we have a function, a polynomial in our polynomial ring here, and if K is its splitting field over F, then the group of F automorphisms of K is called the Galois group of F of X over F. So this one here is just a group of F automorphisms of E, but if E is a splitting field of a polynomial over F, then that would be a Galois group of F of X over F. As an example to see how the elements of this Galois group can be, I show you the Galois group of a polynomial F of X over R. So we take an element in the field of complex numbers written as A plus IB, where A and B are real numbers, and take sigma to be in this group. Then sigma takes one element of C and it sends it to another element of C. So because it is an automorphism, this we can write the sigma A plus sigma I times sigma B. And because A and B are in R, which where sigma keeps all the elements of R fixed, then this goes to A and sigma B goes to B. So we have A plus sigma of IB. Now our main problem here is to find what it is sigma of I, because we cannot send it strictly to I because this is not an element of real numbers. By doing some simple calculations, we find that sigma I is equal to plus minus I. So there are only two possible R automorphisms of C, which sends one element to itself or to its conjugate. So two elements, the cardinality of this group is equal to 2. So dimension of C over R, it is 2. So that means that it permutes the elements of C. The really important theorem, it's fundamental theorem of Galois theory. Using this theorem, we can see that one-to-one correspondence between field theory and group theory. That's it, like E is an extension of F, and all of the other F sub I, F sub 2, F sub I's are extensions of F and subfields of E. And this theorem sets a one-to-one correspondence between these subfields of E and their corresponding Galois groups by satisfying these 5 properties that are here. That is like one of those. If F of 2 is a normal extension of F of 1, then its corresponding Galois group, it is a normal subgroup of the Galois group of F sub 1. And the fifth is the isomorphism, and their dimension and the fixed fields can all be determined by just looking at this one-to-one correspondence. Let E be a Galois extension of F, so it is finite, it's normal, and it's separable extension of F. Then we call E a cyclic extension of F if its Galois field it is a cyclic group. A cyclic group is a group that is generated by one of its elements. To see it better, I wrote an example here. I took this polynomial x to the n minus 1, which is monic and irreducible over the field of rationals. And I found an extension E, which is Q adjoint W, where W is the root of this polynomial. And now, because it contains n roots, I know that it is finite and it is separable and normal extension, because if this is the splitting field of this polynomial, and if it's finite, then it's also a normal extension. It is separable because all of the roots, as we can see here, 1, w squared till wn minus 1, are distinct from each other. So E is the Galois extension. And as we see this group, 1, w squared till w to n minus 1, it is a cyclic group because it is generated by one of the roots, w. So this extension, it is a cyclic extension. To continue further, we need to know the definition of a primitive nth root of unity. If we have a field E and n to be a positive integer, then an element w in E is called the primitive nth root of unity in E if w to the n is equal to 1, but w to the m is different from 1 for any positive integer m less than n. The main theorem of the cyclic extension is this one. It says that if let f contain a primitive nth root of unity, then the following are equivalent. That is, E is a finite cyclic extension of degree n over f. And then the second one, E is the splitting field of an irreducible polynomial x to the n minus b in this polynomial ring f adjoint x. Furthermore, E is generated by f and alpha, where alpha is the root of x to the n minus b. So them being equivalent, it means that from 1 implies 2 and 2 implies 1. The proof of this theorem is not that hard. We can prove this theorem by using the definition of cyclic extensions and the definition of a polynomial being irreducible over some field. For those who want to know the proof of this theorem, you can contact me after the presentation. I'm not going to give any proof of theorems. I'm just going to give the results and some examples for you to maybe see it more easily. Okay, the last extension that I'm going to give a definition is a radical extension. So an extension E of a field F is an extension by radicals or radical extension if there are elements alpha sub 1, alpha sub 2 till alpha sub r in E and positive integers n sub 1, n sub 2 till n sub r such that E is generated by F and those alpha i's, where alpha sub 1 to n sub 1 is in F, and alpha sub I to the n sub I, it is in an element of this extension F adjoint alpha sub I till alpha sub I minus 1, where I is between 1 and R. I wrote an example here, maybe to understand it better. I wrote polynomial x cubed minus 2 times x cubed minus 5, which doesn't have roots in Q. It is irreducible over the field of rational numbers. Now we can easily see that the extension, which it is generated by the root of these polynomials, it is a radical extension of Q because we can find like one of those, let's take alpha sub 1, it's cube root of 2, and that n sub 1 be a positive integer 3, then the cube root of 2 to the third, it is in rational numbers, as it is here. And then we can take alpha sub 2 to be cube root of 5, and alpha sub 2, and n sub 2 again to be a positive integer 3. Then this is an element of its the other extension of Q of the polynomial x cubed minus 5. Useful fact about radical extensions is that if E sub r is a radical extension of f with intermediate fields E sub 1 till E sub r minus 1, which are contained inside of each other, then there exists a radical extension E sub s prime of f with intermediate fields, as we can see here, such that it satisfies these three properties. E sub r is contained in our new radical extension. Our new radical extension is normal extension of f, and its intermediate fields are splitting fields of a polynomial of the form x to the n sub I minus bi, for I from 1 to s. Here I gave an example of how we use that remark, but before that I'm going to give the definition. What does it mean for a polynomial to be solvable by radicals? A polynomial f of x over a field f is said to be solvable by radicals if its splitting field E is contained in some radical extension of f. So our example says that show if an irreducible polynomial p of x over a field f has a root in a radical extension of f, then that p of x is solvable by radicals over f. So here we need to show that its splitting field, it is contained in some radical extension of f. By the previous remark here, if we have a radical extension, I can find another radical extension which contains E sub r. So I draw the diagram here. Let f and let p of x be a irreducible polynomial over f, and E sub r be a radical extension of f. Then by remark, I can find a radical extension E sub s prime which contains E sub r, and it is normal over f. So if alpha is a root of p of x contained in E sub r, then alpha, it is also contained in E sub s prime. But because E sub s prime is a normal extension of f, and it contains one of the roots of p of x, what does that mean? That means that p of x splits into factors here, into linear factors in this radical extension. So E sub s prime contains a splitting field of p of x. Therefore, p of x is solvable by radicals. By definition. To continue further, we need to recall a result from group theory. A group G is solvable if and only if G has a normal series with abelian factors. Further, a finite group is solvable if and only if its composition factors are cyclic group of prime orders. We denote those by this notation here. Why do we need this? Because we are going to make now a connection between field theory and group theory to show that f of x polynomials are solvable by radicals over some field f. To continue, we assume that all of the fields are of characteristic 0. Then our main theorem here is Theorem Four, which I named it Theorem Four, and it says that if f of x is a polynomial in our polynomial ring, is solvable by radicals over f, if and only if its splitting field E over F has a solvable group, Galois group here. The proof of this theorem is long, but it's not that hard. It uses the fundamental theorem of Galois theory, and it uses this theorem here about cyclic extensions. Before I continued here, because we are going to mention Galois group, I gave an example which shows that if f of x has r distinct roots in its splitting field E over F, then the Galois group of f of x, it is a subgroup of the symmetry group S of R. So to solve this, first take f of x to be a polynomial in our polynomial ring, and assume that it has r distinct roots, alpha sub 1 till alpha sub r. Then we set a mapping from the Galois group to the symmetric group SR such that f takes sigma to this phi sub sigma. To show that this Galois group is a subgroup of the symmetric group SR, it is enough if we can show that f is an embedding of the Galois group of f into SR. That is, if we show that it's a one-to-one and homomorphism, then we know that SR contains a copy of our Galois group. So its image, it's a subgroup of a symmetry group. It's easy to see that this is a homomorphism. And also to show that it is identity, we just show that its kernel, to show that it is one-to-one, we just show that its kernel is identity. What does that mean? F of sigma is equal to identity. So phi of sigma is equal to identity. And phi of sigma of alpha I is equal to sigma of alpha I. So it means that sigma has to be equal to identity. So because kernel now is only identity, for sigma to be equal to identity, then sigma takes alpha sub I to alpha sub I. So the kernel is identity. And this implies that F is one-to-one. So F is an embedding of the Galois group of F into SR, symmetry group SR. We can recall from the group theory that the symmetry group Sn is not solvable if n is greater or equal to 5. Thus, we can, from here, any polynomial whose Galois group is Sn for n greater than 5 is not solvable by radicals. So here we can immediately say for some polynomials if they are solvable or not by connecting this result from group theory. This theorem helps us define some polynomials of degree prime, which are monic irreducible polynomials over the field of rationals, to see if they are solvable or not. What the theorem says that if we have f of x, a polynomial over q adjoint x, to be a monic irreducible polynomial over the rational numbers of degree p, where p is a prime, and if this f of x has exactly two non-real roots in the field of complex numbers, then the Galois group of f of x is isomorphic to the symmetry group S of p. To see how we use this theorem, I gave an example here, which says that show that the polynomial x to the 7 minus 10x to the 5 plus 15x plus 5, it is not solvable by radicals over the field of rational numbers. So first of all, to use this theorem, we need to show that f of x is monic and irreducible polynomial over the rational numbers. How do we do that? We use Eisenstein's criterion. We already see that this is a monic polynomial because a sub 7 is equal to 1. To show its irreducibility, we take p equal to 5, p prime, so p squared doesn't divide 5. 5 divides minus 10 in 15, and 5 doesn't divide 1. So this polynomial is irreducible over the field of rational numbers. Moreover, by using intermediate value theorem, there are 5 real roots, one in each of the intervals here. One is in minus 4 to minus 3, minus 2 to minus 1, minus 1 to 0, 1 to 2, and 3 to 4. So we found 5 real roots, and the degree of this polynomial is 7. So there are exactly 2 non-real roots. And now we can see that our polynomial satisfies the condition of this theorem. It is a monic irreducible polynomial of over the rational field, so the field of rational numbers, and it has degree prime, which is 7. It has exactly 2 non-real roots in the complex field. So its Galois group is isomorphic to the symmetry group S7 here. And then if we go here to the Theorem Four, what did we say? We said that a polynomial is solvable by radicals if and only if its splitting field E has a solvable group. But now our Galois group is S7. So 7 is greater and equal than 5, which it is not a solvable group. So the polynomial given here is not solvable by radicals. This was all that I was going to talk to you about today. Thank you all for listening. If you have any questions, I can take them.
Teşekkür ederiz Antigona. Çok güzel bir sunumdu. Sorumuz var mı Şeyma?
Teşekkür ederiz hocam. Ben de teşekkür etmek istiyorum. Ben görmedim chatte de YouTube'da da bir soru. Soruları olan varsa yazabilir arkadaşlar.
Sorusu olan varsa evet. Sanırım soru yok. YouTube'dan da kontrol ettim. YouTube'dan gelen bir soru yok.
Pardon, ben bir soru sorabilir miyim acaba?
Tabii ki, tabii ki. Buyurun.
Hı hı. Ben YouTube'dan dinliyordum da bu polinomları radikallerle çözemeyeceğimizi söylüyor bize Galois teorisi. Acaba bunları çözmek için başka yöntemler var mı? Bunlar hakkında bir şey biliyor musunuz?
Okay. Ben mesela şu an sadece e, bu teoremi kullanarak yani onların Galois gruplarını sadece bakarak solvable olabildiğini gösterebileceğimi biliyorum. Şu an olarak başka bir yöntem bilmiyorum. Sadece bu teoremi olarak gösterebileceğimi biliyorum. Bir de en kolayı mesela bu derecesi asal sayı olan ve onların e, root Türkçesi nasıl bilmiyorum.
Kökü diyebilirsiniz ya da
Ha,
root
tamam.
anlıyorum.
Evet, root. We can okay, so we can say that it is solvable for all the polynomials of degree prime, and if they have those exactly two complex roots. Otherwise, we can check all of the roots of the polynomials in the Galois group, and then by this definition here, if we can show that that group is solvable, then we can immediately say that it's solvable by radicals. Till now, I just know this theorem.
Okay, thank you very much. Very good talk.
Thank you very much for your question.
Başka sorusu olan yok sanırım. Evet, şöyle Discord sunucumuzu da ekleyeyim ben. Eğer katılmak isterseniz oradan bu konular hakkında tartışmak isterseniz de. Şöyle. Çok teşekkür ederiz.
Ben teşekkür ederim.
Çok güzel bir sunumdu. Şöyle bıraktım. Gelmek isteyen arkadaşlarımız varsa katılımcılarımız arasından buradan Discord sunucumuza da katılabilirsiniz. Teşekkür ediyoruz.
Teşekkür ederim.
Teşekkür ediyoruz hocam.
İyi günler.